In this video, we want to talk about antiderivatives. Now, we've talked a lot about derivatives, but now we want to look at something very similar with antiderivatives. Now, if you remember back when we looked at the mean value theorem in section 4.2, we talked about corollary 3. And corollary 3 said, if the derivative of f of x and the derivative of g of x are equal, then there just is a constant that is different between the two functions. And we proved this earlier, so I'm not going to go through it again. But if you remember, this is like saying if we have our function x is x squared and our function g of x is x squared plus 2, then the derivative of each of these is 2x. So this corollary told us that if this is true, that if two functions had the same derivative, they only differed by this constant. So we're going to use that here as we go and we talk about antiderivatives, inverse derivatives, if you will. So a function f, notice this is a capital F, is an antiderivative of a function f of x, lowercase f, if the derivative of the capital equals a lowercase, for all x in the domain of f of x. So in the case we just looked at, so we understand the notation, we are calling the derivative, the thing we take the derivative of, our capital F. So back here, this would be our capital F, and then the derivative of that would be our f of x. That's kind of all the notation means. We wouldn't use these here, okay? So let's look at what this means. So, given a derivative, f prime of x, find all possible f of x functions. So this is take the antiderivative. Find f of x. Now, we know our derivative rules. So based on our derivative rules, when we take the derivative, we subtract 1 from our exponent. So when we take the antiderivative, we're going to add 1. So that means this becomes an x to the 4th. Now, there's a couple ways to think about this, how you do the next part. And I'll explain it kind of the two ways. If you go by the rule, you add 1 to the exponent, leave the 4 there, and then whatever your exponent is, you divide by that to get your antiderivative. So let's go with the 5. This is, you can think of this as x to the 0. So you add 1 is x to the 1st. This is your new exponent, so you divide by that. And then you would get, these would cancel, and you would get x to the 4th plus 5x. Now, another way of doing this, I'll just kind of write this up here. Another way of doing this would be like, let's find our function. And to think about this, we add 1 to the cube, which would be x to the 4th. And then we think about, what do I need to put in front so that when I take the derivative of this, I end up with what I have here. So that would be 4x cubed. Well, I know if I bring down the 4 and subtract 1, I get 4x cubed, so there's my answer. And if I have just 5, I know I need 5x. So this is not so much following a rule. This is kind of you just work out what you need. So let's try again here. Kind of once again talk about both ways. So we have 3x squared. This is going to become x cubed. 3 just stays there. And then my new exponent is to the 3rd power, so I divide by 3. I have 6x. I'm going to add 1 to the exponent, which was going to be 2. My new exponent is 2, so I divide by 2, minus 7x. The other way to think about it, we'll do it the same for a couple here, is I have 3x squared, and that just becomes x cubed, because when I take the derivative, I bring down the 3. Plus, this is x, so this is going to be x squared, and I know when I take the derivative, I'm going to bring down a 2, and I have to end up with 6, so that tells me I need a 3 in front, so when I bring down the 2, I have a 6, and then 7x. And you can see if we came back here and we simplified this, we get to there. So in some of these that are fairly easier, these polynomials with just kind of integer values, you can almost think about it in your head. As these exponents maybe get more complicated with fractions and those kind of things, you may want to use the rule. So we'll kind of have both. So let's look at 3. We have x cubed, so that's going to become an x to the 4th. But you can see there's nothing in the front except a 1 there. So when I take the derivative and I bring down a 4, I need something to cancel with that 4 to make 1. That would be 1/4, or I can divide by 4 if I follow the rule. This is 7x. That becomes x squared. The 7's there. I'm going to bring down the 2, so I need something to cancel that. So that's you divide by 2, and you minus 5x. Now, one thing to consider on all of these is we've actually done all of these incorrectly, because this is not the only function that has that derivative. By our earlier mean value theorem, we have to contend with there's a possibility there could be a constant there and have the same derivative. So the derivative, the antiderivative is not x to the 4th plus 5x, it's x to the 4th plus 5x plus c. So this is our antiderivative. We have to add that plus c because any value you put there, 1, 7, -10, it would still have the same derivative. So anytime we're finding all possible functions, finding these antiderivatives, we need to include on all of these plus c. Okay. Antiderivative plus c. So that number could be any constant. We don't know what it is, but we always have to take, when we find all possible antiderivatives, we have to include plus c. All right, let's look at some more. So f prime of x is 2e to the 2x plus sine. So my function, we know the derivative of e to the x is e to the x, so that just says e to the 2x. Now we have to think about that 2 in front, and we look down here and say, okay, when we take the derivative of e to the 2x, that's going to kick out a 2, which is that 2 right there, so that's my answer. And now we want to take the antiderivative of sine. We know the derivative of sine is cosine, but the antiderivative sine is going to be minus cosine. Because when you take the derivative of negative cosine, the derivative of cosine is negative sine, 2 negatives cancel to give me a positive sign, and then we finally need our plus c. So as we do these, we're now going to have to think about not only what is the derivative of sine, what is the derivative of cosine, we're also going to have to go and remember the antiderivative, where the signs are different. So let's look at minus cosecant cotangent plus 1 over x plus 3x. So first, to find our function, we have to remember that cosecant, negative cosecant cotangent is the derivative of what function, and that is cosecant. Now, when you have something like this, you want to think about this as x to the -1. And then when we add 1 to this exponent, we would say, well, we would get x to the 0. But x to the 0 does not make any sense. And so if you do this and you can't remember what I'm about to say, if you ever have this where you have x to the negative 1 and you add 1 and you get x to the 0 and you think that's just not right, that should be bells and whistles going off in your head to remind you that the antiderivative of 1 over x is natural log. The derivative of natural log is 1 over x. So antiderivative is natural log. And like I said, the way to think about that is if you convert this to this, and then you get x to the 0, and you should have question marks, and that should be enough to remind you, oh yeah, that's natural log. Plus 3x, that would become 3x squared, and then we have to divide by 2. And then we always need a plus c. So we have to add the plus c if it is just find all antiderivatives. But let's say we have this. Find f of x if f prime is 2x and f of 2 is 1. So now we're not finding all antiderivatives, we're finding a very specific antiderivatives. So if we think of this and we have f prime is 2x, then our function is x squared plus c. But if we think about all of the x squared plus c's, so imagine I have this is x squared plus 0, x squared plus 1, x squared plus 2, x squared plus 3. I only have the integer values. I do not have the values, there'd be an infinite number of these. And you can see here is 1, here is 2. And this tells us that this goes through the point 2, 1. So if I look, 2, 1, there is only one function that goes through that point. And then if we tried to trace that function, you could see that that would be this quadratic. So it looks like from a graph 1, 2, 3. Now, how can we find that? We're not going to do that by graphing. That's too hard. So what we know is if f of x is x squared plus c, f of 2 is 1, we can say f of 2 is 2 squared plus c equals 1. So c is negative 3. So that tells us that our function is x squared minus 3. So if you are given some point here that we need to use, sometimes those are called initial conditions or conditions. You're given some condition that f of 2 is 1. You use that to find what c is. If it says find all possible functions, then you have to include the plus c. Let's look at another one. F double prime is 6x minus 6. Now, in this case, we have the second derivative. So if we have the second derivative, we're going to have to find the antiderivative twice. So if f double prime, a second derivative is 6x minus 6, we can find the first derivative, which would be x squared, then I need a 3 in front, minus 6x plus c. And then I want to use what I know about the first derivative, f prime of 1 equals 1, so I can substitute that in to find my c. And if I do that, I get 3 minus 6 plus c is 1, so I get c is 4. So that is my first derivative. I know this c value is actually 4. Now, to find my function, I now take the antiderivative of the derivative. And that's going to be x cubed minus 3x squared plus 4x plus... Now, I don't want to use c again in this problem just because I've already used c. So we have a couple options here. One option is just to call it d for another constant. Some people will, instead of doing that, in this kind of problem, they will call this C2, and this back here was C1, just so as these problems can get more complicated in the future, that if we have multiple constants, we don't confuse them. I'm just going to go C2. If you'd rather make it D or some other variable, that's fine. Now, finally, we know f of 0 is -1, and this is pretty easy because 0 cubed is 0, 3 times 0 is 0, 4 times 0 is 0, plus C2 is -1. And you can see 0, 0, zeros. So we get C2 is -1. So our final answer, our function, is x cubed minus 3x squared plus 4x minus 1. So there is the function that has a second derivative of 6x minus 6. The derivative goes through the point 1, 1, and the function goes through the point 0, -1. So that is the section 4.8 on antiderivatives.